In the previous lecture, we derived Flexure formula based on the equilibrium of a structural member such as beam under external loading. We discussed that in order to satisfy summation of moment about x1 axis equal to 0, we will get the moment equal to EI by rho, where E is the modulus of elasticity of the material, I is the moment of inertia, and rho is the radius of a curvature of the point which is under consideration. This equation can also be written as E by rho is equal to M over EI is equal to sigma 3 by x2. Sigma 3 is derived from the equation sigma 3 is equal to Ex2 by rho. So E by rho is equal to sigma 3 by x2. Plugging that ratio, we get this form of equation. Thus, we can also write sigma 3 is equal to mx2 by I. And this is our well-known Flexure equation. In this equation, if we want to find out the fibers which are the most highly stressed, we have to put the value of x3 maximum. And obviously, the case of a rectangular cross-section beam, which is subject to some external loading, the external fiber will be at a distance h by 2. Plugging I is equal to bh cubed by 12 and x3 is equal to h by 2, we can get the maximum flexure stress in the fiber which is furthest from the neutral axis. We can also call the extreme fiber located at a distance c from the neutral axis, and that would give us the stress sigma max equal to the maximum moment divided by the ratio of moment of inertia and the distance c, which is the distance between the neutral axis and the extreme fiber. This ratio is also called flexure rigidity. Please note that in order to find out the maximum stress, we have to put maximum moment. And as an example, if we have got a simply supported beam, the maximum moment in this beam of length L and having the cross section B into H, the maximum moment is WL square by 8. We can now further discuss the application of this formula using some numerical problems. So we are given a beam that has a rectangular cross section and is subjected to the stress distribution as shown. This is a rectangular stress distribution, this is a triangular stress distribution, and this shows maximum stress at the extreme fiber, which is furthest from the neutral axis. The stress magnitude is 2 ksi or 2000 pound per square inch. The cross section of this element is 6 by 12 inches. We are asked to determine the maximum moment at the section caused by the stress distribution by using the Flexure formula and by using the resultant of the stress distribution using basic principle. So we are asked either to use the Flexure formula, which is sigma is equal to m max by s, and we have to work out the maximum moment. And the second part is asking for finding the maximum moment, using first principle. So let us use the equation which we have derived, sigma max is equal to m by s, to find out the maximum moment. So first step is finding out the moment of inertia, which is b h cubed by 12. So that comes out to be 864 inch 4. And now the distance of the fiber furthest from neutral axis is 6 inches. So therefore C comes out to be 6 inches. Plugging the values in this equation, but keeping in mind that our units are consistent. We can let 2 ksi as it is, and in the end, we will get our moment in kip inch. So we plug the values and get moment equal to 288 kip inch, which is equal to 24 kip foot. So this is the first part. The second part is saying using the first principle. So question is how to find out the moment using the first principle. Again, if we consider the same cross section and we assume that the variation of stress is linear, so the applied loading will make the region above neutral axis in compression and the region below neutral axis in tension. So we would have a triangular distribution both above and below neutral axis, but both regions would have opposite stresses. This triangular distribution will have a resultant located at some point within the top region of the beam. Similarly, the region below will have its resultant located in the bottom region. The top region is in compression, as we discussed. The bottom region is in tension. We have to work out the magnitude of compression and tension and then multiply that with the lever arm, and we would get the maximum internal moment. The way to find out the force, either compression or tension, is multiplying the given stress with the area of the cross sections. Since the stress is varying linearly, we can find the average of this stress, which is equal to half time sigma, and multiply that with the area, which is B time H by 2. Please note that tension will be equal to compression because of equilibrium. Once the force is found, then it's very straightforward to find out the lever arm. The lever arm is 2 by 3 of the base of triangle. So that is the location of this compression force from the neutral axis. Thus, 2 by 3 of C is written. We have to make this distance K twice because E is equal to 2 times K, and that will give us 2 by 3 of H. Multiply the tension with the lever arm E and we would get the moment. This exercise is done over here. We have a force. This force can be determined by taking the mean of the stress, which is 2 ksi, and multiplying that with the area, which is 6 times 6. After that, we can find out the location of this resultant force from the neutral axis by multiplying the base of this triangle with 2 by 3. So we get 4 inches. That 4 inches will be doubled up because that is actually the lever arm. So we get 8 inches. 8 is multiplied with 36 and the resulting moment is 288 kip inch. So that's how we can use the Flexure formula or first principle for finding the maximum internal moment. Now in this another example, we are given a simply supported beam subjected to some loading, and this beam has got length 6 meter and the cross section is in the shape of I. The simply supported beam would have maximum moment in the middle, and that is WL square by 8. We are asked to determine the maximum absolute bending moment stress. So as we had a discussion that the maximum stress would be Mmax divided by I by C. So Mmax is WL square by 8, which can be easily worked out. I, in the case of I, we have to find out the moment of inertia of this I section, and that is being done over here using this formula, which is summation of I bar plus AD square. So plugging values in this, and we should be able to get our I, which is 301.3 to 10 to the power minus 6 meter 4. Once I is found, C is 150 millimeter. Sorry, C is 150 plus 20, which is 170 millimeter, and everything should be kept in meters. So therefore 0.170 meter comes and divided by the moment of inertia. Thus we get 12.7 megapascals. It's also asking us to draw the stress distribution over the cross section at this location. So that can be easily drawn. Over here, we have to find out the stress distribution at the lower position of the flange, and then we can join that with the neutral axis to get our stress distribution. These examples enhance our understanding of flexure theory. We will now move towards the derivation of formula for horizontal shear stress. So let us remind ourselves where the shear stress is coming from. Imagine again we have got a beam which is subjected to some sort of loading. So let that be a UDL loading. And we see that the bending moment diagram is parabolic, being zero at the ends and reaching maximum at the midspan. This is in accordance with the simple support conditions. Since the moment is changing as we move from one of the support toward the midspan, it is that change in moment which will generate the shear. The shear force, as discussed previously, is actually the force which is meant to keep the whole section in equilibrium because of this imbalance of the moment. So again, if we take two sections within the half span of a beam, we call one section as section 1 and another one as section 2. The moments at these two sections can be decoupled, and we will get a stress distribution which is shown in this figure. We assume that the region above the neutral axis is in compression. The two sections are separated by the distance dx3, remembering that x3 is the axis along the beam. Since we have assumed that the bending moment at section 2 is bigger than the bending moment at section 1, therefore the compressive forces on section 2 will be bigger than the compressive forces on section 1. This difference in H2 minus H1 can be balanced only by the resisting shear force dF, which is equal to tau times B dx3. Tau being the shear stress, B and dx3 is actually the area on which this force is acting. So we assume that this force is distributed fully on the area B dx3. B is the width of the section. In this example, it is important to notice that the H1 force is the resultant force on our region of interest. In other words, our region of interest is shown as hatch, and the bottom dimension of our region of interest is at a distance x21 from the neutral axis. The top dimension of our region of interest is at a distance c from the neutral axis. Thus, c minus x21 is the depth of our region of interest. And h1 is actually the resultant of all the varying forces on the depth c minus x21. In other words, H1 and H2 are the resultant of these forces which appear in the form of trapezoid. This region of interest can also be shown in isometric view. So we have this whole region, this whole block as our region of interest. We can also consider a small prism within this region of interest and find out the stresses in this prism. The resisting shear force will be facing opposite to the maximum resultant horizontal force H2 in order to satisfy the equilibrium. This resisting shear force is equal to tau B times dx3. So the 3D isometric view gives us better understanding of what's going on. So in order to satisfy the summation of all the forces in the direction h equal to 0, we can write again dF is equal to h2 minus h1. h2 will be equal to the flexure stress times our depth of interest. So sigma 2 times dA, and it will go from x to 1 till c. Similarly, h1 will be equal to sigma 1 dA, and the limit of the integral would be x to 1 till c. Plugging the value of sigma 2 and sigma 1, we get m2 x2 by I dA within the integral, and the integral limit goes from x to 1 till c. Similarly, we have this other integral having m1 x2 by I into dA within an integral, and the limit going from x to 1 till c. Now, we can bring the moment m2 and I outside this integral. This is because m2 and I both are constant corresponding to the area of the section. So at these sections, we have a unique moment, and the moment of inertia is unique for the whole length. Therefore, we can bring the moment and moment of inertia outside the integral. We discussed that dF is equal to tau b dx3, tau being the average shear stress over the differential area. So putting the value of tau b dx3 in this equation, we get tau b dx3 is equal to 1 over I dm x to 1 c x2 dA. If we assume that m2 and m1 are very close to one another, so the difference m2 minus m1 will give us dn. Please note that m2 minus m1 is taken as common term in this equation. So using algebra, we get 1 over bi dm by dx3 and x2 1 till x till c x2 times dA whole integral having a limit x2 1 till c. dm by dx3 is equal to shear, and x2 dA is the sum of moments of the differential areas dA about the neutral axis. So therefore, this can be written as a prime x2 bar, and the term a prime x2 bar is called as the first moment of area, which is given the symbol q. So tau equal to vq by ib is the shear stress equation. Now, just to remind ourselves that corresponding to this horizontal shear at a region slightly above, we would have an opposite shear in order to satisfy the equilibrium of forces. But these two equal forces having some lever arm will cause a couple, and that couple has to be counteracted by another force in the vertical direction. So that has been shown over here. And if we take a moment about A, this horizontal stress times the area into the lever arm dx2 is equal to the vertical shear stress times the area dx1 dx2 and times the lever arm, which is dx3. dx1 dx2 dx3 get cancelled, and we get the horizontal shear equal to vertical shear. So that means to say that this shear will have an equal vertical shear appearing. So for our example, where of a simply supported beam under uniformly distributed loading, when we draw its shear force diagram, that diagram is based on vertical shear force. Corresponding to that vertical, we have a horizontal shear force also present. Let us now discuss the application of this shear force formula. We have tau is equal to VQ or IB. V can be determined by drawing shear force diagram. In order to get the maximum V, we can take the shear at the supports, which in this case is maximum. So V times divide by IB. So I is the moment of inertia, which is BH cubed by 12. B is the width of the beam, which is constant B. And then we have the first moment of area, which is Q, and Q is AY bar. So if our portion of interest, which is shown hatched, is at a distance x to 1 from the neutral axis, and the top dimension of this region of interest is at a distance h by 2 from the neutral axis, we can easily find out the area of this block, which is B times h by 2 minus x to 1, that is the area, and x2 bar can be found by finding the distance of the centroid of this hatched region from the neutral axis. That is x to 1 plus half of h by 2 minus x to 1. That will give us the shear stress distribution. And we can see that this is actually the equation of parabola. Hence, it is easy to appreciate now that the shear stress at the top fiber is zero, and it keeps on increasing as we move towards the neutral axis. If we are interested in finding out the maximum shear stress, we can do that by considering our region of interest as B times H by 2. So V will be maximum shear, I and B are self-explanatory, Q will be B times H by 2, thus x to 1 in this equation will be 0, and we can get the maximum shear stress at the neutral axis. Let us try to solve some additional problems. In this problem, we are given a solid shaft and a tube in figure 7.9a, which are subjected to the shear force of 4 kilonewton. We are asked to determine the shear stress acting over the diameter of the cross section. So, as discussed, tau is equal to VQ over IB. Shear is given to us, which is 4 kilonewton. Moment of inertia we can find for both the sections. B is the width, which will be worked out for both these sections. And finally, we'll find out the Q. So for the solid shaft, we have I equal to pi r4 by 4, and plugging the values, we get this. For the tube, we have pi by 4, the r external 4 minus r internal 4. So 0.05 power 4 minus 0.02 power 4 whole bracket multiplied by pi by 4, and we get this value, which is 4.783 into 10 to the power minus 6 meter 4. Now Q, which is the first moment of area, that can be worked out for both the sections. We have a solid section, and for this solid section, we have y bar equal to 4c by 3 pi. So if we have a semicircular section from the centroid to the maximum diameter region, the distance is 4c by 3 pi if c is the radius of the semicircle. So 4c by 3 pi is multiplied by half of the circle, because half of the shaft is contributing in the shear stress. So plugging the values, we get 83.33 into 10 to the power minus 6 meter cube. In the case of tube, we find out again our Q for the solid region and then subtract the middle region out of it. So we find out the first moment of area for the solid shaft and subtract the inner gap from it. So that's why 4c naught by 3 pi, pi c naught square by 2 is taken. And then we subtract the internal radius, which is 4ci by 3 pi into pi ci square by 2. Thus, we will get 78 into 10 to the power minus 6 meter cube. So V is known, Q has been worked out, moment of inertia has been worked out. Now the width B or the thickness T, whatever we want to call it, in the case of solid shaft is the diameter or 2 times the radius. So that gives us zero point 0.1 and we plug the values and get 679 kilopascals. In the case of tube, we have this thickness T or B twice thickness of the tube. So this region is added to the other region and that gives us 0.06 meter. We plug the values again in the shear equation and get 1.09 megapascals.